So, this is the final lecture on discrete time Markov chain. In the last class, we learned about, that is, first return first spaces probabilities, and how to characterize the properties like transience and recurrence, in terms of these probabilities. Now, we will discuss about this transience and recurrence, that one important property, what is known as the class property. Class properties of states. Recall, a communicating class C is a subset of the state space such that I communicate J for all Ij belonging to C. That means, if it is a suppose we have this state space, maybe this is this state space, and out of that the state space we denote it by V, and there is a communicating class C, and within this class all states will communicate, but there is no communication between any element of C and C complement. So, now if a property is defined for all states in C, then it is a class property. So, if suppose certain properties are satisfied by all states in the class, then these properties are called class properties. So, that way we will see some class properties. So, that is a theorem. All the states in a communication class are of the same type, all transient, all recurrent, and all periodic. We will prove part A and B, part C also can be similarly proved. Suppose C is a communicating class and Ij belong to C, then there what does it mean? Since J is accessible from I and I is accessible from J, so therefore there exists M greater than 0 and R greater than 0 such that Pij M is greater than 0, Pji R greater than 0. There exists some M and small r where these probabilities are non-zero. Now, consider for any n this probability Pii M plus n plus r. So, that is probability of coming back to state I at step M plus n plus r. Now, we can apply Chapman-Kolmogorov equation. So, we can consider first M plus n is the first step, and then from k it will move to state I in r steps. Thus, Pii M plus n plus r is equal to summation over k Pik M plus n into Pki r. Now, this is sum over all k. Suppose we consider one value of k only, that is k is equal to j, then this now this will be no longer equality, but it will be now this quantity will be greater than this quantity, because we are considering only one value of k. So, Pij M plus n Pji, here Pji r. Now, again we can apply Chapman-Kolmogorov equation for Pij M plus n, and that we can write as, that is, suppose first in M step it will go to L, and n step it will come from L to J. So, that way it is summation over L Pil M Pli n, then Pji r, it is already there. Since it is summation over L, we will consider only one value of L, that is L is equal to suppose J. So, that way if I consider L is equal to J, then what we will get, this quantity is greater than equal to Pij M into Pjj N into Pji R. Now I know that this quantity is non-zero, this quantity is non-zero, and their product we can write as alpha. So this way it will be Pjj N multiplied by alpha. So what we got, that this Pii M plus N plus R is always greater than equal to alpha times Pjj N. So that way we started with state II, but if state Jj if we consider, suppose, then also we can show that Pjj M plus N plus R is greater than equal to alpha times Pii N. Let us number this equation as 1 and this equation as 2. So that way we by assuming that there is a communication between I and J and I, so we arrived at two equations, that is Pii M plus N plus R is greater than equal to alpha times Pjj N, and this other quantity Pjj M plus N plus R, that is greater than alpha Pii N. Now suppose state I is transient, then we prove that this is the condition if and only if summation Pii N going from 0 to infinity, that is finite. So this quantity is finite, alpha Pjj N, that is less than equal to Pii M plus N plus R. So that way we wrote this inequality in reverse order, and already we know that taking summation up to infinity, we get that alpha times summation from n is equal to 0 to infinity Pjj N, that must be less than equal to summation of this from n is equal to 0 to infinity. Now this sum it actually starts from when n is equal to 0, this will be Pii M plus N. Therefore this sum will be less than equal to this Pii N from n is equal to 0 to infinity. So that way what we have got is that Pjj N, that summation n going from infinity, that will be less than infinity, that is convergent. That means if this sum is convergent, then this sum will be also convergent. So what does it mean? That means if state I is transient, then state J will be also transient. So that way we showed that if I and J communicate, then if I is transient, J must be transient. Next, suppose state I is recurrent, then what is the condition? This summation of this n step transition probability n going from 0 to infinity, that diverges to infinity. Now we will go back to inequality 2. So from that we will get that Pjj M plus N plus R, that is greater than alpha times this. Now if I take the summation over n of Pjj, then this quantity will be greater than summation Pjj M plus N plus R, because here when n is equal to 0, this will start from M plus N only, Pjj M plus N. Now from this result we will get that this is greater than equal to alpha times summation n Pii N. So if this quantity is infinity, then this quantity also will be infinity. Therefore what we get is that summation Pjj N for all n going from 0 to infinity, that will be equal to infinity, that means that diverges. Therefore state J is also recurrent. We started with state I is recurrent because I and J communicates, therefore state J is also recurrent. So that way we see that recurrence, transience are class properties, and we can similarly prove that periodicity is also a class property. Suppose in a communicating class, if one state is periodic with period d, then all other states will be periodic with period d. So these results are useful in analyzing the steady state behavior of Markov chain. Now we will consider here a periodic change only. Steady state analysis of periodic change also can be done, but for simplicity we omit that. Recall that we have already got that Pij and limit n tends to infinity. Now for transient, if J is transient, then this quantity is equal to 0, and if it is a recurrent, suppose, in that case what we got is for this is equal to Fij divided by mu j. So that one we have established for a recurrent, if j is recurrent, okay. But how to find out Fij, that we will derive now. This theorem, it states that if the state j is recurrent and I communicate with j, then Fij is equal to 1. We will prove this. Now I communicate with j. What does it mean? It implies that there exists m such that Pji or Pij at some time m must be greater than equal to 0. Now this recurrent state j is recurrent, that means it is visited infinitely often with probability 1. So this also follows from the property of Markov chain. Therefore we can write 1 is equal to probability that xn is equal to j for some n greater than m, given that x0 is equal to j. This probability must be equal to 1 because state j is recurrent. Now we condition with respect to some xm is equal to k, so that we can apply the total probability theorem. So this quantity, this expression will be same as summation over k probability of xn is equal to j for some n greater than m, xm is equal to k given that x0 is equal to j. Here all values of k we are considering, that is why we can apply the total probability theorem. Now if I start with this event, so probability of xm is equal to k given that x0 is equal to j into probability of xn is equal to j for some n greater than m, given that xm is equal to k, x0 is equal to j. But using the Markov property, this part will be simply xm is equal to k, because so that way we can write this part. By definition it is the Pjk m, and this one is probability of xn is equal to j for some n greater than m, given that xm is equal to k, because this is earlier. So we are, it is independent of this, therefore we can write like this. Now this quantity we know that this is Fkj, xn is equal to j for some n greater than m, given that xm is equal to k. So that way we can write this as summation over k Pjk m into Fkj. Also we know that state transition probability Pjk m, if we sum over all k, that is equal to 1. Therefore this quantity, if I write this 1 is equal to this and this is equal to 1, so we can get this relationship summation Pjk m into 1 minus Fkj, that must be equal to 0. Now all these are non-negative quantities. So when suppose 1 is 0, other must be non-zero, like that. So I know that Pji m is greater than 0, Pji m is greater than 0. So in that case 1 minus Fij, because I have put k is equal to I, Fij 1 minus Fij, that must be equal to 0. So because whenever this is greater than 0, this 1 minus Fij must be equal to 0, implies that Fij is equal to 1. So that way we established that if state j is recurrent and I communicate with j, then Fij is equal to 1. So we have seen that in the case of recurrent state how to evaluate Fij, that we have shown. Now let us define null recurrent and positive recurrent states. Null recurrent and positive recurrent states. Okay. So recall that for a recurrent state I, the mean recurrence time is given by this mu I. What is this? First return may be at step 1, it may be at step 2, like that. So that way mu I is the summation n going from 1 to infinity n f I n. Now this mean recurrence time, this is the mean recurrence time, it may be finite or infinite. I know what is the definition of recurrent state. A recurrent state I is called null recurrent if mu I is infinity. The recurrent state I is positive recurrent if mu I is less than infinity. So that way we have defined null recurrent and positive recurrent. We have already established that limit probability of Ij for a recurrent state as n tends to infinity, Pij n is given by Fij by mu Jj. Okay. So now if suppose we are considering aperiodic chain only for an aperiodic irreducible positively recurrent Markov chain. Now irreducible means all the states in this chain communicate. Suppose if we consider a particular case where all states are aperiodic, of course aperiodicity will be if one state is aperiodic, all other states will be aperiodic, and it is irreducible, that means all states communicate with each other. And positively recurrent, we are assuming that this quantity is less than infinity. In that case limit n tends to infinity, Pij n is equal to 1 by mu Jj. So that is because since Fij is equal to 1. And similarly also an aperiodic irreducible positively recurrent Markov chain is called an ergodic Markov chain. That is also one definition. So that way we classify one particular class of Markov chain, what is known as ergodic Markov chain, which is irreducible and positively recurrent and aperiodic. We considered when suppose J is a positive recurrent state, but when J is null recurrent state, what will happen? Because this mu Jj is equal to infinity, therefore Pij n will be equal to 0. So therefore what we observe that for a transient state J, this quantity was 0, we have already defined Pij n is equal to 0. Similarly, for a null recurrent state J, limit n tends to infinity, Pij n is equal to 0. Let us solve one problem. This is a 4-state Markov chain. Suppose these states are also, let me call V also 0, 1, 2, 3. So we can draw this state transition diagram. Suppose this is 0 state, 1 state, 2 state, 3 state. Okay. Now from 0 to 2, 0 to 2, there is a transition with probability 1. Similarly, from 1 to 3, 1 to 3, there is transition. This is 1 to 3, there is a transition with probability 1. Then this is 1, and this is 2, 2 to 1, 2 to 1, 2, this is 2, 2 to 1, we have this with probability 1, this is with probability 1. And then from state 3, we have transition to state 1 with probability 1/4. We have transition to state 1 with probability 1 by 8. and from state 3 we have also transition to state 2 with probability 1 by 8. 1 by 8. So, this is 1 by 8, this is 1 by 8, this one is, so 1 0 2, 3 to 1 is 1 by 4, and we have also from 3 to 3 itself there is a path here, that is with probability half. So, this is the state transition diagram. Now, we can see that suppose 0 communicate with 1, because from 0 we can come here, and similarly from 1 we can go here, and then there is a path here. So, that way 0 and 1 communicate. Similarly, we can show that 0 and 2 communicates like that. This is an irreducible Markov chain. This is an example of irreducible Markov chain. So, therefore, if we can prove that one state is recurrent or transient, then all other state will also be similar type. Now, let us consider state 0. We will find the first return probability. Okay. So, for this state 0, how we can come back? From 0 to 2 we can go, 2 to 1 we can come, and then 1 to 3 we can go, and then 3 to 0. Okay. So, that way now this, that is f 0 0, that is the probability that eventually this chain will return to state 0, given that it has started at state 0. So, what will be this probability? It may come only in one step. What are the probability therefore? That is, it may come in 4th step only. For the first time it may come to this state in 4th step. Okay. So, that way this will be equal to this probability is 1 into, then this probability is 1 into this probability is equal to 1 by 4, plus it may come back to this in one more step. Suppose this is it may go here, it may go here, it may go here, and then it may go here and come back. Okay. So, that way we can consider, suppose this step we can consider for the second time. Suppose this is 1 into 1, then 1 into 1, then it will go to 1, and then it will remain there into half, and then come back into 1 by 4. That way also we can approach. So, that way we can find out all the possibility that it will return here for the first time, and then we can show that this probability is equal to, ultimately we can show that this probability is equal to 1. So, that way if f 0 0 is equal to 1, therefore this state is recurrent, and since this Markov chain is irreducible, all these states will be recurrent. Now, we will state one powerful theorem, that is, all states of an aperiodic irreducible Markov set with state space finite space. All states of an aperiodic irreducible Markov chain with the state space V is equal to 0, 1 up to n minus 1. It is a n dimensional state space, finite, is positively recurrent. All states of an aperiodic irreducible MC with finite state space is positively recurrent. So, that is, if there is communication between all the members of the states and the state space is finite, then it will be always positively recurrent. Now, for such a Markov chain, the limits pi j is given by this. So, limit pi j, that is, if I consider pi j, that is equal to limit of Pij n as n tends to infinity, and I know that this is equal to, it is 1 by mu jj, this is suffix mu jj for j is equal to 0 to n minus 1 form a probability distribution. So, what we claim that this limiting probabilities Pij n as n tends to infinity, that we have derived that it is 1 by mu jj, and this is a this form a probability distribution. So, this is a probability distribution first part, and it satisfy the equation pi 0, pi 1, pi n minus 1, that is the probabilities is equal to pi 0, pi 1, pi up to pi n minus 1, this is the probability vector multiplied by p. That means, at the limiting stage, suppose any state probability is that state probability multiplied by p. So, this was the statement, this we used in earlier, suppose in the case of steady state analysis using eigen values, we derive this relationship. So, similarly here also now we are able to say where these steady state probabilities will be existing and what are the values of those steady state probabilities. So, where it will be existing if the all states are aperiodic and positively recurrent and all states communicate with each other. In that case, for a finite Markov chain, finite space, that means if state space is finite, then a steady state distribution will exist, and that steady state distribution is given by this equation. First of all, the above relation, this relationship is true only for positive recurrent states, as we know that this quantity is 0 for a transient and null recurrent states, that we have already derived. So, that way this is true only for positive recurrent aperiodic state. Now, let us see the other part. I know that for a state transition matrix, you consider any row sum, summation Pij n j going from 0 to n minus 1, that must be equal to 1. So, therefore, if I take the limit as n tends to infinity, then also this sum must be equal to 1. Now, since it is a finite sum, I can take limit this limit inside, that is the requirement of the finite Markov chain. So, I can take the limit inside. So, what does it means? That summation limit of Pij n as n tends to infinity must be equal to 1. Now, I know that this quantity is pi j. So, that pi j summation over j equal to 0 to n minus 1 must be equal to 1. Okay. So, therefore, if this limit exists, then this sum must be equal to 1. So, what does it mean? So, summation of pi j going from 0 to n minus 1 is equal to 1. Therefore, these pi j's must be a probability distribution. So, that way we have shown that this is a probability distribution, but it has to satisfy that transition probability relationship. Suppose this distribution pi j, suppose this is a probability distribution. If you multiply it by P matrix, we should get pi j only. So, this is suppose pi, okay, pi vector, then this should be also pi vector. So, that is the relationship we have to prove. Now, we consider the CK equation Pij n plus 1, that is equal to Pjk n into Kj summation over k going from 0 to n minus 1. We are applying the Chapman-Kolmogorov equation for n plus 1 step, and we assume that it first go to state k in step n, then from state k to state j it goes in one step. That way we derive this. Okay. Now, we can find the limit as n tends to infinity. So, limit of Pij n plus 1 as n goes to infinity, that must be equal to, we will take the now limit inside the summation. So, Pik and Pk into Pkj. Okay. Now, I know this limit is equal to pi k because it is a recurrent state. So, this limit is pi k into Pkj. So, this quantity is Pkj. So, that will be valid for j is equal to 0, 1 up to n minus 1. So, that way we arrived at the equation that steady state probability after transition, one step transition, we will get the same value. So, in matrix form we can write this row matrix pi 0 pi 1 up to pi n minus 1 is same as pi 0 pi 1 into pi n minus 1 multiplied by p. So, that way we prove the theorem. Thus, we have a way to analyze a Markov chain with finite state space and which is irreducible, aperiodic and positively recurrent, then it will have steady state probabilities, and these probabilities will be given by this equation. Of course, we will have the constraint that summation of these probabilities is equal to 1. Now, let us summarize the class. We derived that all the states in a communication class are of the same type, that means all transient, all recurrent and all periodic. Then also we showed that if state j is recurrent and I communicate j, then Fij, what is this? Fij is the probability that starting with state I, it will cross state j eventually. So, that way this probability is equal to 1, that we establish. For an aperiodic irreducible positively recurrent Markov chain, this limiting probability Pij n is equal to 1 by mu jj. This is the mean recurrence time. And for a null recurrent state, limit of Pij n as n tends to infinity, that quantity is equal to 0. So, earlier we proved that this is 0 for a transient state. Finally, all states of an aperiodic irreducible Markov chain with this state space, this that is a finite state space, is positively recurrent. So, there is a finite probability, finite steady state probability. For such an MC, the limits pi j is given by this 1 by mu jj. For j is equal to 0 up to n minus 1, and this quantity for different j, they form a probability distribution, and this distribution satisfy this equation, that is this steady state probability vector is same as steady state probability vector multiplied by p. So, that way the condition that where this will be satisfied if all states are aperiodic, irreducible, and the MC is of finite sample space and it is positively recurrent. Thank you.